Welcome back, grade 10s. In this lesson, we will continue with revision of matter and classification. We're going to start off by learning the microscopic representation of pure substances and mixtures. Now, the word microscopic indicates to us that whatever we're presenting can only be viewed under a microscope. That's not necessarily the case here because we are not able to see atoms under a microscope. This is the best representation of an atom that has been achieved. It happened around the time of COVID at Cornell University that they managed to magnify a type of crystal by 100 million times. And so we can see that this crystal is made up of atoms. Each circle here represents an atom, but microscopically, using a microscope, we are not able to see any more detail of an atom. In other words, we can see that the atom is round, but we cannot see electrons, protons, and neutrons. So when we microscopically represent atoms or molecules, what we need to realize is that we cannot actually see them under a microscope. And those microscopic representations are simply drawings that allow us to assess what the real situation might look like. So usually it's impossible just by looking at a substance to know if it is a pure substance or if it is a homogeneous mixture. Remember that a pure substance is only made up of one type of atom or molecule. A homogeneous mixture is made up of more than one pure substance, but in the case of a homogeneous mixture, it looks the same throughout. So by just looking at a pure substance, by just looking at a homogeneous mixture, it's not possible for you to know what it is made up of. Is it a pure substance? Is it a mixture? Is it made up of elements? Is it made up of compounds? So as a result, we make microscopic representations of atoms or molecules. And that is simply a mental picture that we create, again, because we cannot actually see atoms in any detail under a microscope. So here's the microscopic structure of a solid, liquid, and gas. And you should be familiar with this kind of diagram. Now, when you draw a microscopic representation of a solid, make sure that the particles are never actually touching, because based on the particle model of matter, the first thing that the particle model of matter tells us is that all matter is made up of particles. The second thing it tells us is that the particles are always moving. The third thing it tells us is that the particles are never touching. And the fourth thing is that there is a force of attraction always between the particles. In the case of a solid, there's a very strong force of attraction. In a liquid, there's a strong force, but not as force as in a solid. And in the gas phase, the forces of attraction are very, very weak. So because the particle model of matter tells us that the particles are never touching, when we draw them, we should draw them in such a way that they don't touch. Now, what is a macroscopic level? Well, if microscopic level is the level of the very small things, the macroscopic level is where we discuss big properties, things that we can actually see, like the state of the matter. We can see if a substance that's in front of us is in solid form or liquid form or gas form. We can use a thermometer to measure the melting point and the boiling point of different substances. That is macroscopic. Those are the big properties that we can actually see and we can measure them. But microscopically, we're talking about tiny, tiny things, things that we cannot even see with the aid of a microscope sometimes, which is the case with atoms and molecules. Now, microscopically, We say that the particles of solids are arranged very close together. They have very small spaces between them, but remember that there are always spaces between the particles. In a solid, the particles that make up the solid are arranged in a regular pattern. They vibrate in their position. They don't have freedom of movement, but they do vibrate in their position, and they have very strong forces of attraction between them. The particles of liquids are close together still, only 10 times further apart relative to the particles that make up a solid. They have small spaces between them. We say that the particles of liquids slip and slide past each other, and they have strong forces of attraction between them. Now, the particles of gases are spread very far apart, about 1,000 times further apart relative to the solid phase. They move freely and randomly, and they have very weak forces of attraction between them. Diatomic molecules are two of the same element bonded together. And this is how these molecules exist in nature when they're alone, unless they're bonded to something else, forming a compound or a different molecule. So let me explain what I mean by that. Well, if you consider the periodic table, firstly, let's identify our diatomic molecules. And it's really simple. If you create the number 7, starting from nitrogen and going down to iodine. So here we've got nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are 6 of the 7 diatomic molecules. And then the 7th diatomic molecule is hydrogen over here. So it makes a lot of sense to mark off your diatomic molecules the moment you receive a periodic table on a test or on an exam. So these are 7 diatomic molecules. All of them exist as gases at room temperature, except for bromine, which is a brown liquid at room temperature, and iodine, which is a purple solid at room temperature. So essentially what this means is that when you're breathing in oxygen, you're not actually breathing in an oxygen atom. Oxygen atoms do not exist on their own in nature. You are rather breathing in O2. You're breathing in diatomic oxygen. So you're breathing in 2 oxygen atoms that are chemically bonded to each other. So oxygen will never exist in nature as O on its own. And when you're breathing in oxygen, you're breathing in O2. And that applies to all the diatomic molecules. Now, oxygen, an oxygen atom, can bond to, say, a nitrogen to form nitrogen monoxide. So that's not to say that oxygen cannot exist as a single oxygen atom within a compound, but oxygen cannot exist as a single oxygen atom just floating around. So oxygen will either be bonded to itself, in which case it is a diatomic molecule, or it will be bonded to something else, but it will never be found as a single atom in nature, and that applies to hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So the microscopic representation of a diatomic molecule in the gas phase looks like this. Now, because this is a diatomic molecule in the gas phase, there are big spaces between the molecules, and each molecule is represented as a diatomic molecule, so it's 2 atoms of the same type that are chemically bonded. Over here, we have the microscopic representation of water in the liquid phase. So here is the O, and here are my 2 H's. Each water molecule is represented as an O with 2 H's attached to it, and the particles are quite close together, yet not in an organized pattern because this water is in the liquid phase. I would now like you to try to provide some microscopic representations on your own. So at this point, I'd like you to pause the video and try this exercise on your own before you return to this presentation to look at the answers and the explanations. So firstly, a mixture of two types of compounds in the liquid phase. Well, the liquid phase tells you that they've got to be close together. The particles that make up the liquid have got to be close together, but not in an organized pattern. Now we've got two types of compounds. Remember that what defines a compound is two or more different types of atoms. So here I've got one compound, and here I've got another compound. So I've got two types of compounds because this is made up of two types of atoms, and this is made up of two types of atoms. So both of these substances that I've drawn here represent compounds. And again, based on the arrangement, they're in the liquid phase. A mixture of an element, a diatomic molecule, and a compound in the gas phase. Well, an element's a single atom. A diatomic molecule is two of the same type of atom, and a compound, well, we've just discussed it, you have to have at least two different atoms within that compound, and because it is in the gas phase, large spaces between them. So here I've got my element, my diatomic molecule, and my compound. Pure iodine. Well, we know that iodine is a diatomic molecule, and we also know that iodine exists as a solid. So here I've drawn iodine as a solid. The reason that this is the solid phase is because there is an organized pattern to the iodine molecules. Note that I place the molecules in an organized pattern and very close to each other, but there are always gaps between the molecules. That is because, based on the particle model of matter, the particles that make up matter, they don't touch, but there are very strong forces of attraction in between the molecules. And lastly, a mixture of helium and hydrogen. Well, helium is a noble gas, therefore it doesn't react and it exists on its own. Hydrogen's a diatomic molecule. Both helium and hydrogen at room temperature exist in the gas phase. So this is my representation of my helium atoms, and here I've got my hydrogen diatomic molecules. Large spaces between them because they're in the gas phase. Now that brings us to metals, nonmetals, and metalloids in the periodic table. So let's now delve a little bit more deeply into the periodic table. So the elements in the periodic table are arranged in columns and in rows. Columns go from top to bottom, up and down, up and down. A row, on the other hand, goes from side to side, so left to right. The columns of the periodic table are known as groups. So here we have a group. This is group number 1. So each group has a number from left to right. Group number 1, group number 2, group number 3. And in total, there are 18 groups. The rows of the periodic table are known as periods. And each period has a number from the top to the bottom of the periodic table. So this is the first row, which is made up of hydrogen and helium. So that's period 1. Then we've got period 2. And over here we've got period 3. And in total, we have 1, 2, 3, 4, 5, 6, 7. Therefore, there are 7 periods. Interestingly, if you look at these 2 rows at the bottom of the periodic table, Well, look at period 6 over here. It starts with element 55, 56, 57. Then it moves straight on to 72. So actually element 58 to 71, they belong over here. And period number 7 starts with element 87, 88, 89. And so this row over here actually belongs as part of period 7. The reason that they're separated all the way at the bottom of the periodic table, we will briefly understand a little bit later. We may use the group and period numbers to describe the location of an element in the periodic table. So, for example, we can see here that calcium is in the second group and in period 1, 2, 3, 4. Now, you can say group 2, period 4, or you can say period 4, group 2. It doesn't make a difference provided that your group number is correct and that your period number is correct. The elements in the periodic table can be classified into 3 groups: metals, nonmetals, and metalloids or semimetals. Now, you may call metalloids semimetals, you can call semimetals metalloids. Those words are interchangeable, but you obviously need to be familiar with both. Let's start off by discussing metals. So most elements in the periodic table are metals. Metals are silver gray in color, but there are 2 exceptions to that, and those exceptions are copper and gold. So most metals simply look like this, but gold and copper have distinct colors. All metals are solid at room temperature, but there is one metal that is a liquid at room temperature, and that metal is mercury. The chemical symbol of mercury is Hg. Let's talk about the characteristics of metals. So metals reflect light when they are polished. They can be hammered without breaking, meaning that metals are malleable. They can be stretched into thin wires, meaning that metals are ductile. They have high melting points. They are good conductors of heat, good conductors of electricity, and they have high densities. However, some metals reflect light better than others. Some metals are better conductors of electricity than others. Some metals are more malleable. Some metals are more ductile. So we can say that some metals have stronger metallic properties than other metals. Now, this is a generalization. Generally speaking, metals that are more to the left-hand side of the periodic table have a stronger metallic character, and metals that are further down the periodic table also tend to have a stronger metallic character. Let's now talk about nonmetals. At room temperature, nonmetals may exist as solids, like carbon and iodine are both solids at room temperature, as gases like nitrogen and oxygen, and bromine is the only nonmetal that exists as a liquid at room temperature. Let's talk about the general characteristics of nonmetals. Nonmetals do not reflect light. They are poor conductors of heat, poor conductors of electricity. They have low melting points, and they are brittle. Noble gases are nonmetals in group 18 of the periodic table. Helium, neon, argon, krypton, xenon, and rhenon are all examples of noble gases. Noble gases get their name from their unique property that they do not combine with other elements to form molecules or compounds. They don't combine with each other either. And this is because they have a full outer energy level. Now, you wouldn't understand what that means yet, but we're going to get to it a little bit later on in this topic of matter and material. This brings us to metalloids or semimetals. Now, in the periodic table, metals and nonmetals are separated by a zigzag line or by steps. So take a look here. Here are the steps, and you should always put them into your periodic table the moment that you get your periodic table, starting on the left-hand side of boron and then continuing all the way to the bottom. This zigzag line over here is very, very helpful because it tells us a few things. So firstly, it tells us that elements found along the zigzag are metalloids or semimetals, but we need to be aware of one exception, and that is aluminium. Even though aluminium over here touches the zigzag line, it is not a semimetal, but rather it is a metal. So let's take a look now at this periodic table and mark off a few important things. We start off with a zigzag line, knowing that any element that touches the zigzag line, with the exception of aluminium, is a semimetal. Now, if you look at the first point on the slide, it says that metals and nonmetals are separated by the zigzag. Okay, so what that means is that all the nonmetals exist on this side of the zigzag. So let's take a look here. These are all nonmetals. These are noble gases. All of these over here also nonmetals. And these phosphorus, nitrogen, and carbon. So anything on the right-hand side of the zigzag is a nonmetal, but also don't forget hydrogen. It is sitting here on its own. It is not a metal. It is one of the nonmetals. So as you can see, this zigzag line helps us to identify our semimetals. And by identifying our semimetals, we can easily identify our nonmetals. And what does that mean for the rest of the elements? The rest of the elements are all metals. The other thing that I told you should always do is make the number 7, just so that you do not forget your diatomic molecules from nitrogen to iodine and not forgetting hydrogen. And by doing this, it makes the periodic table a lot more manageable to work with. You've also got your group numbers here already, but when you receive a periodic table, you should also add the period numbers from number 1 to 7. Metalloids have properties of both metals and nonmetals. Some are dull, some are shiny. Now remember that nonmetals are dull and metals are shiny. Some semimetals are brittle, like nonmetals. Others are malleable and ductile, like metals. But what we can say about the characteristics of metalloids is that all metalloids are solid at room temperature. They are good conductors of heat, though not as good as metals are. They are poor conductors of electricity at room temperature. This is very important. Semimetals are good conductors of electricity at higher temperatures. So at room temperature, they're poor conductors. But when the surrounding temperatures are higher, or when the semi-metal itself gets hotter, then it becomes a good conductor of electricity. So metalloids are semiconductors, and it's important to be able to explain what this means. So it means that they are poor conductors of electricity at room temperature, but they're good conductors of electricity at higher temperatures. This video over here shows a beautiful experiment with silicon and how silicon conducts electricity at higher temperatures but not at room temperatures. Now, the periodic table on the next slide is the one that you'll receive on every test and exam all the way to matric. And what I already told you is that it's a really good idea to label your periods. Your columns are already labeled. It's a good idea to put in your zigzag lines. The number 7 for your diatomic molecules. Don't forget hydrogen. You can also mark off your semimetals, remembering to leave out aluminium, which is not a semimetal, but rather a metal. And it also makes a lot of sense to mark off all your nonmetals on the right-hand side of the periodic table.